Alright guys, this is going to be a little different than the other videos. I'm basically going to go through the notes that I sent you via email, so if you haven't printed those out yet, I would definitely print them out and have them by you as I go through this. It's really not a difficult topic, you just need to see a couple of examples and you'll understand what it's doing. Alright, so I'd kind of like to start with a graph real quick. And if you see here, we have the graph of f of x is right here. It's the curvy looking thing. And I've identified a few points on f of x. There is a point A and a point B. And those corresponding x values for point A and B are little a and little b. And the corresponding y values, f of A, f of b. What I've done is drawn a secant line through the points A and B. And I've also drawn a tangent line to the curve f of x. And all the mean value theorem says is what is down here. It says that if you have a function f of x and it is a continuous function over a given closed interval and it's a differentiable function, so you can take the derivative and evaluate it over an open interval, same open interval as the closed interval, so using a and b as the endpoints, then there must exist a c. So there's some number c where c falls somewhere between a and b, where f prime of c is equal to f of b minus f of a over b minus a. And this is the most usable form of this. Algebraically, you can cross multiply and take the b minus a and multiply it by the f prime of c and get this formula down here. This itself is called the mean value theorem for derivatives. And the reason why it's called the mean value theorem is it's talking about average, mean value for derivatives. The right side of this equation is really just an average. It's f of b minus f of a over b minus a. It's like average velocity if this was a velocity problem. It's your displacement over time type of relationship. I think the translation that you guys need, just to make sure you understand it, is simply this. The mean value theorem for derivatives says somewhere on that open interval AB, there's an x value that we're calling c, where the tangent line's slope is equal to that of the secant line through A and B. So that, and I can't go back to the screen, but I'll draw it for you again, that if you have some interval from A to B, the secant line that connects the 2 points has to have a parallel tangent line, and this value right here is going to have a c value that falls somewhere between A and B. We're looking for that c value. And in fact, these are the questions that we need to be able to answer to deal with the mean value theorem. Not very difficult. The first question is what you're trying to do. For any given function, can you find the value of c? And you can only do this if there are two things that are true. First thing that needs to be true: the function must be differentiable on AB. You must be able to take the derivative and evaluate the derivative over the entire interval, and the function must be continuous over that interval. If you have a discontinuous function, there is no guarantee that this will work. As with most of the math we do, sometimes it's best looked at in an example. So here's an example. Determine all the values of c on the given interval which satisfy the conclusions of the mean value theorem for the function f of x equals 5 minus 4x on the interval from 1 to 4. So before I go about actually doing this, I want to make sure that my function is both continuous and differentiable on the interval 1 to 4. I know that the only domain restriction is going to occur when I deal with the x in the denominator. So if x was able to take on values of 0, I would be in trouble, but 0 is not on the interval from 1 to 4, so I know I'm continuous on that. And for the same reason, the function is differentiable over that entire interval, because when I do take the derivative, I'm going to get an x squared in the denominator, which again would not be differentiable at 0, but that's not in the particular function's domain, so I don't have to worry about it. The calculations are extremely easy for the mean value theorem. So here's my generalized equation for the mean value theorem. I would like to find the value of c, this value right here, such that the derivative evaluated at c is equal to the secant line slope. So my endpoints of 4 and 1, I'm going to get my f of 4 and f of 1 values. which end up being 4 and 1, oddly enough, by plugging them back into f of x. So that I have f prime of c equaling f of b minus f of a all over b minus a. So I'm looking for where f prime of c is equal to 1. Well, what's f prime of c? It's the derivative evaluated at this number c. Well, the derivative of 5 minus 4 over x is 0 plus 4 over x squared. But I'm doing that at c, so I'm going to replace the x with a c. So 4 over c squared. So I'm left with f prime of c, there it is, equaling f of b minus f of a over b minus a, which is just the value of 1. And I need to find the value of c on the given interval. Well, by solving for c, I get plus or minus 2. But remember, the domain that I'm working on is a and b going from 1 to 4. So that means that negative 2 is not in the domain, so I don't have to worry about it. So I only go ahead and report c equals 2 as the answer. So that is the value guaranteed by the mean value theorem on the interval 1 to 4. Here's a second example, nice polynomial function over the interval negative 2 to 4. So I know that all polynomial functions are not only continuous, but they're also differentiable. So this shouldn't be tough to do. My f of a and f of b values, so 0 minus negative 6 is 0 plus 6, 4 minus negative 2 is positive 6. And the derivative of f is just 2x minus 1, so 2c minus 1 has to equal 1, which means that c is equal to 2. I'm sorry, c is equal to 1. 1 is definitely in the domain from negative 2 to 4, so I have found a value in that domain that is guaranteed by the mean value theorem. And that's it. For example number 3, you have a rational expression, x plus 1 over x, on the domain negative 1 over 2. And for this one, I cannot use the mean value theorem to find a value of c. And the reason is this is not a continuous function, nor is it differentiable over its entire domain from negative 1 to 2. The function is not defined at 0. So since x equals 0 is not in the domain, I cannot use the mean value theorem. So therefore, there are no values of c guaranteed. If you were to look at the graph of x plus 1 over x and consider trying to draw a tangent line from negative 1 to 2, let's see here, give yourself a pen. You would have, something that looks like that, where here is negative 1 and here is 2. So here's your A and here's your B. So here's your secant line. And there is no guarantee that there is any line that is parallel to that is tangent to the curve. So kind of out of luck due to the discontinuity. All right, for the last one, here's the function, here's the domain. It's polynomial, so it is continuous and differentiable. Generating the secant slope, so f of b minus f of a over b minus a, right here, and right here just reduces to 4. And the derivative is 3x squared plus 4x minus 1, so 3c squared plus 4c minus 1. Set it equal to 4. And then to solve for c, remember, we're going to have to bring that value over and set it equal to 0. And the only difficulty here is just remembering that you have ways to do this. It's a non-factorable trinomial, so you're going to have to use the Pythagorean quadratic formula. The quadratic formula. So here is the quadratic formula set up. We know that the quadratic formula will result in 2 roots. I don't know what the square root of 76 is, but I know it falls somewhere between 8 and 9. So I would say that negative 4 plus or minus 8.5 over 6 would be the values, but I only need to consider the value of c that fall between negative 1 and positive 2. So if it was negative 4 minus root 76, that's going to be way too small to give me a value between negative 1 and 2. So the value that I would use is the positive value, negative 4 plus radical 76 over 6. So that is the mean value theorem for derivatives. Again, it's take the derivative, set it equal to the slope of the secant line, find the missing value that is making that a true statement, or missing values if there's more than one. Just be careful to not get tricked into doing it for something that's not continuous or differentiable on the given interval. But otherwise, that is all there is to it. Oh, perfect timing. End of class. Bye.